starting off here, I want to identify the different parts of this right here. Obviously, it's a monomial because it's a one-term polynomial, but just some of the anatomy, starting with that 9 right there. We know that anytime you have a number, a real number that multiplies with a variable, we refer to that as the coefficient of that particular term. So the 9 there would be the coefficient, and then that there, the 4, of course, is going to be exponent associated with the variable. Remember back in the day we talked about the fact that that entire expression, the x to the 4th, we refer to that as the power. And then, of course, the x itself, so just this right here, you might call it a variable, or you might call it just the base of that particular power. So you can call it the base, and of course it's also known as a particular variable. So jumping down to here, when we think about multiplying each of these expressions, or to simplify the product, what we're trying to do right here is we're trying to multiply 2 to the 2nd with 2 to the 4th. Now, if you just kind of think like what 2 to the 2nd means, it of course means 2 times 2. And you think about what 2 to the 4th means, of course it means 2 times 2 times 2 times 2. And then because of that dot right there, right, you're going to multiply. And so what does that mean when you multiply 6 2's in a row, right? It means 2 to the 6th. So isn't the answer the same thing as 2 to the 6th? Right? And so if you think about this just kind of generally, like if you take some number and then you multiply it with another same number, and this is like to the m power and this is to the n power, right? Could you say that that's going to be x to some certain power? And it turns out you certainly can, because really these numbers right here are just keeping a tally of how many times you're timesing the x with itself. And so really the total tally is actually going to be m plus n in terms of what we get right there. And you can see that that holds right there with the 6 because it came from the 2 plus 4. So clearly right here that's going to be the same thing as 5 to the 8th. Now if you actually wanted to like figure out what those numbers are, of course you can. That's going to be some ginormous number. I don't have a calculator on me right now, so it is whatever it is when you plug it in. I know off the top of my head right here this would be the number 64 when you do 2 to the 6th there. So that's really useful when we're multiplying polynomials with one another to recognize those properties of exponents. So right here you have an x to the 2nd and an x to the 3rd, and you're trying to multiply these together. So you can just use that property of exponents, right? This means x times x, and this means x times x times x. And if you're multiplying all that together, really you just end up with 5x's multiplied, right? So that would end up being x to the 5th overall. Be careful, because if you had like a problem like this, like x to the 2nd and x to the 3rd, but you were trying to do a different operation, so maybe like a plus or a minus, it turns out that that would actually be simplest, right? Because there you're trying to combine like terms, and they're not like terms, so that's actually already in simplest form. With this next example right here, really you can think of this as like 2a to the 6th, and then you got that parentheses 4a to the 6th, so clearly you want to multiply those two things that I underlined. So since everything's just multiplying, right, there's no adding, subtraction, or anything, we know that multiplication is commutative, associative, all that sort of stuff. So like the 2 and the 4, like clearly we're going to be able to multiply them together to become 8, right? And then we can also take the a to the 6th and multiply it with a to the 6th, and becomes a to the 6 plus 6, or in other words, a to the 12th. And that would be the final simplified expression right there. Basically the same thing right here. That's really a -1, right? So that's going to be able to times with the 7 to give you -7. And then you're also going to be able to times like m with m to the 3rd, which would be m to the 4th, of course, and then n to the 4th times n is n to the 5th, right? And that ends up being the simplified form of that expression. So there we were multiplying two monomials with one another. So now what we want to get into is involving polynomials with a little bit more terms. So it does turn out that we can kind of generalize the distributive property, because when we've learned about the distributive property before, we've really just said like if you have a times just like a b plus c, then it does equal a times b plus a times c, of course, right? So if you wanted to generalize that and say let's have b plus c plus d plus however many things, like can the a distribute to all of those things? And the answer is yes, of course, right? So that's really useful for us to be able to multiply polynomials with one another. So here it says to multiply, and that w right there, you can definitely multiply to each of the terms right there. So when you multiply w times 4, you do get w times 4, but by commutativity of multiplication, right? That's the same thing as 4w. And then the other part right there is a w times a negative w, which is minus w squared. So it is equal to that upon distribution. Now, with polynomial answers, we usually want to write it in standard form. So if you rearrange this to write it as negative w squared plus 4w, that would really put the answer there in standard form then. With the next one, this is where you can distribute to more than just a couple things. So when you do the first part of that distribution, negative 3 times 5 is negative 15. And then you also have the n times the n to the third, which does give you n to the fourth. And then there, a negative times a negative will become a positive 3. And then n times n squared is n to the third. And then finally, negative 3 times 8 is negative 24. And then that n also distributes there. And the last part right here, I just want you to recognize that here you can kind of use distribution backwards, because if you think about it, if I times that with that, right, by commutativity of multiplication, specifically referring that multiplication symbol, right, can't you rearrange around that multiplication symbol there and write it like this, and then it looks more like a standard distribution, right? So like when you distribute like that, is it any different than if you distribute like that? And the answer is absolutely not, right? So you can distribute backwards, like I was saying. So if you take that, 6 times 2 is going to be 12, and x squared times x to the fifth is x to the seventh. And then when you distribute to there, 6 times 7 is 42, and x times x to the second is x to the third. And then that would be your simplified form, and that's also in standard form because the exponents go in decreasing order. And then a quick little problem right here that asks for what is the product of 2x squared and x plus 1. So a product, of course, means the answer to multiplication, right? So you're really trying to multiply and find the product of 2x squared with x plus 1. Now the thing is that you want to multiply with the quantity of x plus 1. So if I just write it like that, that's not what we want to have happen, because you get an answer of like 2x to the third plus 1 if you did that, but that's not what we want to do. We want to multiply with what the result of x plus 1 is. You have to have that in parentheses, and then you always want to get a simplest answer in math, right? So you're going to have to distribute to get a simplest answer. So when you distribute, you're going to get 2x to the third, but then 2x squared times 1 is 2x squared, and that right there would be a polynomial that's in standard form and also the simplified answer.